Okay, so as I mentioned before, on Monday discussion, I kind of finished up the nomenclature with the other half of the class. So I want to kind of do the same thing with you, so everybody's at least officially in person on the same sort of topic. Uh, and hopefully that will be good. So last time where we finished up talking about nomenclature, we were talking about really ionic compounds and how to go about naming those guys. Remember, there's really two types of ionic compounds that we sort of classify, which are type 1 and type 2. And basically, they're both ionic. And that means that they both have, as we talked about today as well, with bonding metal and a non-metal. And as we talked about today as well, we get that transfer of electrons from our metal to the non-metal. It creates that cation, which is positively charged, that's attracted to our anion, which is negatively charged. Again, no sharing of electrons in these type of compounds, the complete kind of attraction of the opposite charges that hold them together. The main difference between type 1 and type 2 really is the metal. And whenever you're naming anything that involves a metal and a non-metal, it is always the metal that's most important. If it is a type 1, it basically means that the metal has a fixed positive charge. And if you remember, those are pretty much our group 1, 2, and 3 on the periodic table. Also our silver, cadmium, and zinc, which are transition metals, but they do have, again, a fixed positive charge. Once you identify those guys as sort of being a type 1 metal, that's pretty much all you need to do. You don't have to worry about figuring out charges or anything like that. You just use the whole name of the metal. And the non-metal is, guess that IDE at the end of it. So again, if we looked at something like CaCl2, by looking at this, which is calcium, and that is chloride, calcium is group 2, which means it has a fixed charge of +2, and that's all you have to worry about. You just proceed with the whole name, which is calcium, and obviously chloride. The other important thing we talked about is, again, even though there are 2 here, really the 2 is there to balance out the charge. And as we talked about today, really to make sure everybody gets to that octet rule, or 8 electrons. It has no effect on the name. You should not use any prefixes or anything like that. You could have as many as you want there. It would still just be called chloride at the end. Type 2 is basically the same deal, except that the metal pretty much has a very positive charge. Sorry, very positive charge. And those are typically our transition metals, except for obviously the 3 that are up here. And in addition, things like tin, lead, in that sort of area of the periodic table, even though they're technically not transition metals below the staircase, they can have multiple types of charges. The only different thing that we do here is we do have to figure out what the charge is on the metal so we can tell people what we're dealing with. And then we proceed to basically do the same thing. We take the whole name of the metal. We do use Roman numerals here to indicate the charge on the metal, and then the non-metal gets the IDE treatment. So if we had FeCl2, when we look at this, Fe is iron, which is a transition metal. So that automatically should just kind of signal to you that you need to figure out the charge. So we'll go, okay, I don't know what the charge is. As we talked about, you will always know what the charge is on what it's bound to. So that is Cl, which is group 7, and it has a -1 charge, and there are 2 of them, which gives us a grand total of -2. That means that the iron here does have to be +2 to balance it out. And what we would do is basically just incorporate that into our name. And this would be iron Roman numeral 2. And again, it would be chloride, no prefix, the 2 for the positive charge that we see up there on the metal. Any questions on that stuff? I think we talked about last time altogether. So as we talked about today, ionic compounds, again, the purpose of when we do put the formulas together for ionic compounds is to make sure that we do end up with an overall charge of 0. And really the purpose of that, as we talked about today, is to make sure, again, everybody achieves that noble gas configuration. We want to also do that, again, I think I mentioned it last time, but we do want to do it in the simplest way that you could put those guys together to get to 0. There's many different ways, obviously, you could put them together to get to 0, but the correct way to do it in terms of the formula of an ionic compound is basically the simplest way that will get the overall charge to equal 0. So why don't we take a look at a few here just to refresh our memory. So let's say we had CrBr4. Let's say we had K2S. Let's go with CuO. And let's do iron 3 phosphide. And let's do magnesium oxide. And let's do aluminum nitride. All right. Take a couple of minutes. Guys on the left, correct name. Guys on the right, correct formula. Look at CrBr4. When I see Cr, I know it's a metal. I see Br, it's a non-metal. So automatically I know it's an ionic compound. So I would need to decide really, is it kind of type 1 or type 2? And that is always going to be determined by the metal here. That is chromium, which is right there in the middle of our transition metal region. So that also should tell us it's type 2 because of that guy. Also should tell us that we do need to kind of figure out the charge. So we do have 1 chromium. We do have Br, which we know is group 4. I'm sorry, group 7, and there's 4 of them. That means that we actually have 4 of those -1s. So to balance it out in this case, the chromium would have to be +4 to balance out, again, all 4 of these guys that we got going on, basically. That means that's all we need to know. We're going to go with chromium. We're going to a Roman numeral 4 because of the positive charge. And again, even though there's 4 of the Brs, it is just bromide at the end. Again, no prefix or anything like that. Any questions on that one there? Coming next, we have K, which is potassium, which is a metal. Our S is sulfur, which is a non-metal. When we look at our metal here, it is potassium, which is group 1, which means it has a fixed charge. And that tells us automatically it is type 1. That pretty much means I don't have to worry about anything. I'm just going to call it what it is. So even though there's 2 of them, it is still only called potassium. And sulfur becomes sulfide, IDE at the end of it. Remember, there's no prefixes or anything used in this type of naming. Lastly, here on the left, we got Cu, which is copper, O, which is oxygen. So copper a metal, oxygen a non-metal. Copper is a transition metal. In this particular case, we do need to figure it out because it's type 2, but we actually have 2 of them since I added the 2. The oxygen is group 6, which has a -2 charge. That means in this particular case, each copper is actually +1 in this case. And that would mean that the name here would be copper Roman numeral 1 for the individual charge, and oxygen would become oxide. Question on any of those 3 there? When we are going from name back to formula, that gives us a lot of information. I see iron Roman numeral 3. That automatically tells me that the iron has a +3 charge. The phosphide is phosphorus on the periodic table. That is group number 5, which actually has a -3 charge. That means when I put these together, I actually just need one of each of those, right, to get to 0. And that will give me FeP in this case. Yeah. Question on that one. Magnesium oxide, I don't see a Roman numeral, tells me it's type 1, also tells me it is a fixed charge, so I just need to find magnesium on the periodic table. That is group number 2, which tells me it does have a +2 charge. Oxide is oxygen on the periodic table. That is group 6, which also actually has a -2 charge in this case. So again, in this case, I actually just need one of each of them. MgO would be the correct formula in this case. Magnesium with a +2 would be our cation, right? And our anion here would be our oxygen with a -2 charge. Question on that one. Lastly here, aluminum and nitride. Aluminum, which is group 3, tells me it has a +3 charge. Our nitride, which is group 5, has a -3 charge. I did not pick very well on these. Again, in this case, we end up with, or maybe I did pick well, depending on your perspective. We just need one of each of those, gives us Al and N in this particular case. Any questions on any of those type 1 or type 2 guys? Yeah. Okay. All right, so then we're going to continue on to the next type of naming, which is type 3. So let's take a look at those guys. Obviously, what we just saw there is what's summarized on this screen. Again, only those guys in group 1, 2, 3. And again, you can add zinc, cadmium, which are always going to be +2, and silver, which would be +1. Do not need Roman numerals. And then obviously everybody else there in the transition metals will need the Roman numerals. All right, so let's get into that we just did. Type 3. Type 3 compounds are a little bit different. They are what we talked about today as well. They are molecular or covalent compounds. These are our 2 nonmetals together. And in this case, we are having sharing of electrons. And as we talked about today, will be equal or unequal sharing of electrons. These are absolutely, I would think, the easiest to do, but they're also the ones that most people screw up on because they want to do all kinds of weird things and stuff like that. So when we name type 3 compounds, this is actually where we do use prefixes. So this is actually where you should use prefixes, is actually in this type of naming, not in any other type of naming. We use prefixes like mono, which means obviously 1. Di, which means 2, tri, which means 3, tetra, which means 4, penta means 5, hexa means 6, hepta means 7, octa means 8, nona means 9, and deca means 10. So we use these prefixes because there's really sharing of electrons here. We kind of do a very simple one. We give a prefix to the first guy, we give a prefix for the second one. And there's a couple of things that are slightly different that we do here. But the nice thing is you really don't have to worry about balancing charges or what charges are. You pretty much just need to count and use the appropriate prefix. So first off, we prefix up the first name, and the first element we use the whole name. So the first one, whole name and the appropriate prefix. The second one we prefix, and it gets like a normal non-metal name that ends in IDE. So first one, whole name, second one, IDE, attach the appropriate prefixes. There are a couple rules. The first major rule is we do not use mono on the first name, but you can use it on the second name. It's okay. So if we had something like CO, that is a non-metal, that is a non-metal. There's only one of each of them, which technically means they both get mono. We would not use on the first name, so we would just use the entire first name of the element. The second guy, it is okay to use the prefix. So we could use mono, and he also gets the oxide part of it. This also brings up another important thing that happens is, as you can see here, sometimes the prefix will lead you into kind of two vowels in a row, and we usually don't want that. We don't usually call it carbon monoxide, right? We usually call it carbon monoxide. So we typically will drop the O from the prefix, and the correct name here would be carbon monoxide. So that's a very common thing that occurs in sort of type 3. You use a prefix, you get a couple of O's that come together. First O gets killed there. You get a prefix that ends in an A, and the next one starts with an O. We get rid of the A from the prefix. Two I's are okay. People are happy with the two I's. I don't know why, but we usually will leave the two I's. So those are a few little things that we kind of do when we're naming these guys. Get rid of a vowel if we get two in a row, except for two I's. And we don't use mono on the first one, but definitely can use it on the second one. And it's really that sort of simple. You don't have to balance anything, don't have to figure out charges, literally count how many you have and pick the appropriate prefix. Here are again the prefixes, along with again a couple of those things that we get rid of. Is definitely the A into an O, or two O's back to back, we do get rid of it. Now, as we also talked about, I think the other day as well, there are certain things that do have sort of common names in addition to sort of getting rid of those prefixes. H2O is water, and it's not a trick question. You should call it water. NH3 is ammonia. And the other one that I think we had on our list was CH4, which is methane. So you don't want to call water like dihydrogen monoxide. So that's, nobody wants a refreshing glass of that, right? So just call it water. The other sort of consideration that occurs with a nonmetal and a nonmetal is when we have hydrogen involved. So when we do have hydrogen involved, since hydrogen technically is a nonmetal, and when it kind of hooks up with another nonmetal, it is actually really not named like a type 3 compound. It's actually more named like a type 1 compound, an ionic compound. So when we got something like that, where we have hydrogen, like HCl, even though technically speaking, they are sharing electrons, and technically speaking, it is a covalent compound, and everybody's sharing electrons, we almost envision this as two ions together, H plus and Cl minus. So we actually will name this very much like we would do type 1, and then we would call this hydrogen chloride. So hydrogen is kind of a weird one. We really don't kind of name it when it comes first and it's positive, like other nonmetals and nonmetals that come together, really because a lot of them will end up as being acids, and there's certain other things involved with it. So even if you have, for example, two of the hydrogens, H2S, we would still just call this hydrogen, and then the second guy is named like a normal nonmetal, and this would be hydrogen sulfide. And it's really thought of almost like an ionic compound, like you got two H pluses and an S2 minus. So hydrogen is one weird exception, that it is a nonmetal. We don't really follow sort of the nonmetal rules for naming it. So if you have hydrogen, it sort of comes first like that, especially when it's attached to another nonmetal, and it comes first, it's pretty much hydrogen, whatever the second guy is how we name it. Any questions on that there? Okay. All right, so why don't you take a second here and name those guys, and then why don't you also write the formulas for these? So I'll do a little better here, hopefully. Dinitrogen, pentoxide. Let's do carbon hexafluoride. And let's do dioxygen tribromide. All right, so correct name on the left and formulas on the right. Kind of be the fastest ones that you do, as long as you don't try to do anything weird. So when we look at this, we see iodine, which is a nonmetal. We see oxygen, which is a nonmetal. So that should automatically make you happy that pretty much you don't have to figure out anything except pick the right prefixes. So obviously 2 is di and 7 is hepta. And remember, we will go with di and the entire name there, the first element, which would be diiodine. The two I's are okay in this case. Oxygen on the second name there gets the IDE treatment. We will get an A and an O that backs up. So we just want to drop the A off of the prefix there. We end up with diiodine heptoxide there. Question on that one. Coming down here again, we see carbon, which is a nonmetal. We see oxygen, which is a nonmetal. Again, we just want to roll into prefixes. Prefix for 1 would be mono. Prefix for 2 would be di. Do I use mono on the first name? I do not. So we're just going to go with carbon in this case. Second name does get the prefix and the IDE. So that would be our carbon dioxide in this case. Lastly, looking down here, we see phosphorus as a nonmetal. We see chlorine as a nonmetal. Again, 1 for the first one, which would be mono. Tri for the second one. Just like above, we will not use mono on that first name. So we'll use phosphorus and tri. And again, chlorine becomes chloride. Any question on any of those names? Now, personally, I think the next set here is really the easiest of all of them. It is going from the name back to the formula. As soon as you see di and penta, basically, you have nothing to figure out other than write what it says. So di means 2, nitrogen means N, so that's an N2. Penta is 5, oxide is oxygen, O5, and that is it on that. So again, nothing to balance here because they are nonmetal. Nonmetal is sharing electrons. Same thing here. We don't really see a prefix on the first one, which is carbon, but we definitely do see it on the second one, which is hexa. So that tells us no prefix on our nonmetal carbon in this situation means there's only one of them. So we would write a C. Hexa is the prefix for 6. Fluoride is F. So this would be CF6 in this case. And lastly here, we see some prefixes, di and tri. So di is 2, oxygen is O, and tri is 3, Br3. Again, nothing to balance in this particular case. Any question on any of those type 3 guys? At no point do you see me using any type of Roman numerals here, right? So just prefixes for these guys. If you find yourself doing a Roman numeral and a prefix together, it is probably wrong. So you should not be doing that. So everybody has sort of their place. Type 1, no Roman numeral, no prefix, just the name and the IDE. Type 2 is the only place where you use really a Roman numeral per se. And again, prefixes here for our type 3 guys. Any questions on type 3 guys? All right, the last type of naming is everybody's favorite. Not really. All right. There's our rules that we just talked about. Let's talk about polyatomic ions. Polyatomic ions are actually groups of nonmetals together that actually are sharing electrons, like we just talked about in bonding, and has an overall charge. So they are still ions, but oddly, they're ions that are actually held together by covalently bonding to one another. So for example, if we look at something like NH4NO3, this is actually 2 polyatomic ions here. That is NH4 plus. That 1 nitrogen and 4 hydrogens stay together. The overall charge is +1. We actually drew it earlier. It is this guy, I believe we drew. That is our Lewis structure that we drew earlier. That is what we're dealing with here. That is why the nitrogen and the 4 hydrogens stay together. They're sharing electrons. They move around as one unit as they go from one place to the next. This guy here is another polyatomic ion, which is NO3 minus. The 1 nitrogen and the 3 oxygens has a -1 charge. I think we drew that guy as well today. And it looks like this. This is also why the nitrogen and the 3 oxygens stay together. They're sharing electrons. They move around as one unit. Although they are things that share electrons, they do have an overall charge, which makes them ions as well. So basically what we're doing here is putting together 2 ions. We're putting together an ion that is positively 1 charged and negatively 1 charged, which means we basically just need one of each of those, which is how we get to our formula of NH4NO3 in this particular case. Each of these polyatomic ions have special names. This is what is known as the ammonium ion. Not to be confused with ammonia that does not have a charge. And this is the nitrate ion. The good news about polyatomic ions is you pretty much just use the names. So since we put these guys together, put them together here, this guy would be known as ammonium nitrate. Would be the name. Now, in most cases, the polyatomic ion will probably be negative. Most polyatomic ions are negative. There's a few positive guys along the way. So what ends up actually happening when we're dealing with polyatomic ions are they are oftentimes hooked up with metals. So they oftentimes find themselves hooked up with metals. The metals are the positive cations, and a lot of times the polyatomic ions actually are the negative anions. So what that means is because they typically will kind of hook themselves up with metals, we oftentimes will follow like type 1 and type 2 rules that we talked about, which means when we look at the metal, if it needs a Roman numeral, we should include the Roman numeral like we did with type 1. And if it does not need a Roman numeral, we will not include the Roman numeral. And for the negative part of that, it will just be the polyatomic ion name. So let's take a look here at a chart. This is a chart of some polyatomic ions. And there are several that you do need to know, which are what's on these lists here. There's a way that you can sort of memorize them to make them easier. Is there are several that are sort of related to each other, and what we sometimes call like a group of 2 that are related to each other. So for example, if we look at NO3 minus and NO2 minus, which are right here. This guy is nitrate. This guy is nitrite. This guy is 1 nitrogen, 3 oxygen with a -1. This is 1 nitrogen and 2 oxygens with a -1 charge. The one that has the greater number of oxygens in a group of 2 will typically end in 8. The one with the least number of oxygens in a group of 2 will usually end in ite. You could think you ate too much. That's a good way to remember it, the one with the more oxygens. If you look at sulfate, which is SO4 2-, that's a sulfur and 4 oxygen with a -2 charge. That is known as sulfate, ATE. There's one that's related to it, which is SO3 2-. That is 3 oxygens and 1 sulfur with a -2 charge, has 1 less oxygen. So that is sulfite, ITE. So groups of 2 that are related to each other, the one with the most oxygens will end in 8. The one with the least oxygens will end in ite. There is like a group of 4 that are related to each other, which we see here. And that is ClO4-, ClO3-, ClO2-, and ClO-. The only difference between all those is the number of oxygens. They all have a -1 charge. If you break it up by like most oxygen, which is right here and above, the one with the most oxygen, as we can see here, they both end with 8, which is what you would expect. But obviously you can't call them both chlorate because they would have the same name for 2 different things. So in addition, for the guy that actually has the most oxygen, we start with per, and that is referred to chlorate. That is ClO4-. Starts with per, ends with 8 in a group of 4 that has the most oxygen. In a group of 4 that has the least oxygen, which would be coming down this way, they both end in ite, but the one with the least number of oxygens starts with hypo, and ends with ite. So this guy would be known as hypochlorite. So in a group of four, that's the most common group of four that you come across. The guy with the most starts with per and ends with ate. The guy with the least starts with hypo and ends with ite. You can actually swap out this. This is really a halogen, right? So you can swap it out for really any halogen. Its name's similar. So if you had BrO4 minus, instead of perchlorate, that would be perbromate. Just kind of switch out bromine for chlorine in that case as well. Now, a vast majority of the polyatomic ions will end in ate and ite, but there are some that actually end in IDE, like hydroxide, IDE, cyanide, IDE. Another common thing that sometimes occurs with polyatomic ions is we sometimes will put a hydrogen on top of it. So if we take CO3 2 minus, which is carbonate, and we add an H plus to it, we end up with HCO3 minus. We put a hydrogen on it, so we call this hydrogen carbonate. And if that wasn't enough, sometimes people call it bicarbonate. Instead of hydrogen carbonate, they will use the bi instead of hydrogen. You also see that with sulfate. If you put an H plus on sulfate, they will call it hydrogen sulfate or bisulfate. So if you see the word bisulfate or bicarbonate, it basically means you put an H plus on top of whatever it's called, carbonate or sulfate. Any questions on that there? Yeah. Yeah, you should be familiar with most of what's on this list. Yeah. And definitely like on the review sheet, they'll say specific ones that you should definitely know. But for the most part, what's on these tables and the table in your book, you're kind of responsible for. Yeah. Other questions? All right, here's another table, similar table, another one here. We'll go with this one, I think. It's got a little bit more room to write on, I think. All right, so let's talk about, how we go about sort of naming these guys. So for example, if we took NaNO3. So when we look at something like this, that Na is a metal. The NO3, as you will hopefully learn, will be a polyatomic ion, which is right there. So like I said before, basically these guys oftentimes will be hooked up with a metal. So we still want to look at the metal in this situation. The metal is sodium, which means, do I need to use any type of Roman numeral with sodium? I don't. It has a fixed charge. So we would really just start with sodium, the whole name. And this NO3 is nitrate. So it would just be called sodium nitrate. So whole name of the polyatomic ion and the normal sort of naming of the metal. It is really two ions here. It is a sodium ion that has a +1 charge. And it is a nitrate ion that has a -1 charge. So that's why we just have one of each, +1, -1, when we put it together to do so. If I had FeNO3 2 in this case, we would look at this, which is iron. And do I need a Roman numeral on this guy? I do. It's a transition metal. When I look in the parentheses here, that is still nitrate. And that is basically NO3 minus. There is a parentheses and a 2, which means that we don't have one of them, but we actually have two of them, right? Which gives us an overall negative charge of -2. That means that the iron in this case, like normal, to balance it out, does need to be +2. And we would name it very much like what we did with type 2. We would go iron, Roman numeral 2 for the charge on the metal. And again, even though there are two of these nitrates, it has no effect on the name. So very much like type 1 and type 2, we would just call it nitrate. Question on that there. So if we had, say, something, for example, like calcium hydroxide, and we wanted to write the formula, right? We would approach it the same way as we normally do. Come back. So if we want to do calcium hydroxide, we would go with calcium, which is group 2, which is a +2. We would look up on our chart or at some point when you remember, and you would find hydroxide, which is right there at the very bottom in this case. And hydroxide is OH minus. So in this particular case, when we put these together, do I need more calcium or more hydroxides? Yeah, because hydroxide is -1. So to balance it out like normal, we would need 2 of them. So when we write the formula, we would write CaOH and 2. Would I want to write it like that though? I would not, because really when I write it like that, that tells me I have 1 calcium, 1 oxygen, and 2 hydrogens. And that's not really what we've got going on here. We actually have 2 oxygens and 2 hydrogens. So whenever you have more than 1 polyatomic ion, you do need to put parentheses around it and the number on the bottom. And that now tells us we have 2 oxygens and 2 hydrogens, basically 2 hydroxide units. So whenever you come across more than 1 polyatomic ion, you got to put parentheses around it and put the number on the bottom. Question on that there. So let's try a couple here. Maybe we'll go on with this one. All right, so let's go with go with that guy. Let's go with go with that one. So do the names of those 2, and let's do sodium. Let's do sodium hydrogen carbonate. And let's do iron 3. Let's do iron 3 cyanide. Why not? That's on the list. All right. So try the formulas there for the left, and on the right hand side, correct names. C. So we'll start up here on the top right. We got Cu2SO4. So clearly we see a metal. So we want to think about, do we need a Roman numeral? Do we need to figure out the charge? And that is copper, which is a transition metal. It is sort of like a type 2 sort of situation happening here. This SO4 is sulfate, which is somewhere up here right there. So we want to kind of approach the same way. We got a copper. We're not sure what the charge is, but we don't just have 1 copper. We actually have 2. We do know from at some point memorizing the formula there that sulfate will have a -2 charge. That means in this particular case, each copper should be +1 to balance it out, right? +1 gives us +2 to balance out the -2 charge that we see on the sulfate. At this point, we would go with copper, Roman numeral 1 because of the charge. And again, the sulfate here, we would just use the whole name, and it would be copper 1 sulfate. Question on that one there? Coming here, we have Mg, which is magnesium, and we have PO4, which is phosphate, which is right there. Magnesium is really what we should look at since we do have a metal involved. Magnesium is a type 1 metal, which means it has a fixed charge. That means we don't have to worry about Roman numerals, right? And it does have a +2 charge, and that means we could just use the whole name of it, which would be magnesium. Even though there are 2 of these phosphates, it doesn't affect the name, so it would just be phosphate. The reason we got all the numbers there is because, as I think I just saw fingers over there, magnesium is group number 2, the appropriate way. Magnesium has a +2 charge, and there are 3 of them, right? And that balances out the 2 -3 charges that we see over here for the phosphate. basically -6 and +6. So we end up with 0 in this case. So that's what all those things for. We also see that we had more than one of the phosphates. So we did need to put the parentheses around, right, with the number on the bottom so they don't all run together. Any question on that name there? All right, going backwards, we just kind of want to get all the pieces basically and put them together. So sodium is group 1, which means it does have a +1 charge. That is a long name of hydrogen carbonate, also sometimes referred to as bicarbonate, which is right here. And that has an HCO3 minus. Again, the 1 hydrogen and carbon and 3 oxygens in this case, all just has a -1 charge. So ultimately, when we look at this, we're putting together something with a +1 charge and a -1 charge, which means we really just need one of each of them, and it should be NaHCO3. Now, in this particular case, there's just one polyatomic ion. You don't need to put parentheses or anything around it. You could just leave it the way it is in that case. Question on that one there? And to finish up here, iron Roman numeral 3 tells us the iron has a +3 charge. Cyanide, one of those few polyatomic ions that actually don't end in ate or ite, is right here. And that is Cn minus. And again, in this case, the carbon and nitrogen has a -1 charge. So to balance out the +3, we need not 1, not 2, but 3 of those to balance it out. That would give us an iron. Because there's more than one of the polyatomic ions, we do need parentheses and the Cn inside the parentheses with the 3 on the bottom. And we would be in business in that case, yeah. Question on polyatomic ions, how to handle them. Essentially, you could kind of think of them like in most cases is we're going to fall in like a type 1, type 2 type situation. You want to kind of look at the metal, and regardless of how many polyatomic ions you have, you simply just use the name, no matter how many you have. This is really when you have a polyatomic ion would be the only place where you potentially could have like a Roman numeral and a prefix, because the prefix is actually part of the name to begin with. So some of the polyatomic ions in their actual names have prefixes, and that's the only case where you would actually end up perhaps with a Roman numeral and a prefix, because you're just actually just using the name. Any questions on that? That actually should wrap up naming. Now you're all caught up.